All right. Let's try to dive into some pretty fascinating math today.
Yeah.
You know, the Langlands Program and conformal field theory.
Okay.
You sent in some excerpts from a lecture series, and I have to admit this is some next-level stuff.
Yeah, it is.
But don't worry, we're going to unpack it together.
We'll see.
And see if we can make sense of it.
Yeah.
How number theory, geometry, and even physics intertwined in this wild mathematical landscape.
It's definitely a journey.
Okay.
But a journey that has the potential to change how we view the universe.
I'm ready to have my perspective shifted.
Great.
The lecture notes start by talking about polynomial equations.
Okay.
And the quest to solve them.
Mm-hmm.
It even mentions dramatic duels and early deaths among mathematicians.
Interesting.
Is that where we need to start?
It might seem like an odd place to begin.
Okay.
But understanding the history helps us grasp the significance of the Langlands program.
Okay.
Mathematicians like Abel and Galois were obsessed with finding solutions to polynomial equations. Those equations you likely encountered in algebra class.
Right.
Their work, especially Galois, revolutionized our understanding of equations and laid the groundwork for what would eventually become the Langlands program.
So what exactly did Galois do? The notes mention something called a Galois group.
Right.
Which sounds pretty intense.
Galois had this incredible insight.
Oh.
He realized that you could analyze the symmetries of an equation to understand its solvability. He developed the concept of a Galois group, which essentially captures these symmetries.
Okay.
Think of it like a map that shows you how you can rearrange the solutions to an equation without changing its fundamental structure.
So it's not just about finding the answers. It's about understanding the underlying structure and relationships within the equation itself.
Exactly.
Go ahead.
And that's where the Langlands program comes in.
Okay.
It takes this idea of understanding structures and relationships and expands it dramatically.
Okay.
Connecting seemingly unrelated areas of mathematics.
I'm starting to see how Galois' work might tie into a bigger picture.
Okay, good.
But how do we get from groups and symmetries to something as vast as the Langlands program?
It's about finding these unexpected connections and correspondences.
Okay.
The core idea of the Langlands program is that there exists a mysterious link between Galois representations, which capture arithmetic information about equations, and something called automorphic representations, which capture analytic and geometric information.
Whoa.
It's like saying the shape of a musical instrument is intimately connected to the sounds it can produce.
That's a pretty wild analogy.
I know.
I can sort of see how the shape dictates the sound, but how does that translate to math? What kind of connection are we talking about here?
It's a deep and complex connection that mathematicians are still trying to fully understand.
Right.
One way to think about it is through the lens of number fields and function fields.
Okay.
Number fields are the familiar sets of numbers we work with, like rational numbers. Function fields, on the other hand, involve rational functions on curves.
Okay.
What's fascinating is that these two seemingly different types of fields exhibit surprising parallels.
So are you saying there's some hidden structure that governs both numbers and functions?
That's precisely the beauty of the Langlands program.
Wow.
It suggests that there is.
Okay.
And for function fields, the Langlands program has been proven to be true thanks to the work of mathematicians like Drinfeld and Leforgue. However, when it comes to number fields, the Langlands program is still largely conjectural, a tantalizing mystery that mathematicians are striving to solve.
Okay, so we have this potential unifying theory that works perfectly in one realm but remains unproven in another. That definitely sounds like a mathematical thriller.
It is.
But where does the geometric part come in?
Okay.
The outline mentioned something called the Geometric Langlands Program.
Right.
Does that mean we're adding shapes into the mix now?
In a way, yes. The Geometric Langlands program is a reformulation of the original program using the language of geometry.
Okay.
It allows mathematicians to visualize and study the program using tools from algebraic geometry, even over fields like the complex numbers.
So instead of just working with numbers and equations, they're looking at shapes and spaces to try to understand these relationships.
Precisely.
Okay.
And one of the key concepts in the geometric approach is something called moduli spaces.
Okay.
Imagine a space where each point represents a different mathematical object, like a vector bundle on a curve.
Okay.
It's like a vast library where each book contains a different equation or function.
That's a helpful visual.
Good.
And what are we looking for in this mathematical library?
We're searching for patterns and connections.
Okay.
And that's where the concept of Hecke eigensheaves comes in.
Okay.
These are like special signals hidden within these vast geometric spaces.
Right.
They encode deep arithmetic information and are thought to be central to understanding the Langlands program.
Okay, so we've got hidden signals within geometric spaces that hold clues to unlocking the mysteries of the Langlands program.
We do.
This is getting seriously complex.
It is.
But before we get too lost in the mathematical weeds, the outline mentions a connection to physics.
Interesting.
How on earth does physics fit into this picture?
That's where it gets even more mind-bending.
Okay.
The Langlands program unexpectedly shows up in a branch of physics called conformal field theory, CFT,
Okay.
which studies systems invariant under conformal transformations, transformations that preserve angles.
Okay.
These theories are incredibly important in areas like string theory and statistical mechanics.
So are you saying that the same mathematical structures that govern the Langlands program are also at play in the physical world?
It is.
That's pretty wild.
And it's a connection that's still being actively explored. What's particularly fascinating is that certain objects in CFT, called conformal blocks, turn out to be related to those Hecke eigensheaves we were just talking about.
Wow.
It's like finding a hidden bridge between two seemingly separate universes.
Okay, I am definitely going to need a moment to process all of this.
Okay.
We've gone from solving equations to uncovering hidden symmetries, exploring vast geometric libraries, and now we're venturing into the realm of physics.
That's right.
I think we need to pause here and take a breather
That sounds good.
before we dive into the even deeper waters of the Langlands program.
Okay.
Okay, so we've established that the Langlands program is like this mathematical web connecting seemingly unrelated areas.
Yeah.
It's fascinating,
Mm-hmm.
but it also feels incredibly complex.
Sure.
Are there specific examples
I
that
can-
might help illustrate how this all works in practice?
Absolutely. Examples are key to grounding these abstract ideas.
Okay.
Let's start with that historical anecdote about solving polynomial equations.
Okay.
The lecture notes mentioned Cardano and his quest to solve the cubic equation.
Right.
It sounds like there was some drama involved, too.
Yeah, something about mathematical secrets and betrayal.
Well,
Lay it on me.
Cardano was an Italian mathematician in the 16th century
Oh.
who published a method for solving cubic equations.
Okay.
But the catch is he actually got the method from another mathematician, Tartaglia,
Oh.
who had sworn him to secrecy.
So Cardano spilled the mathematical beans.
He did.
Wow.
Cardano argued that the method deserved to be shared with the world
Okay.
and published it anyway,
Okay.
which led to a bitter dispute between the two.
Really?
It's a reminder that even in the world of mathematics,
Yeah.
human drama and rivalries are never far away.
Right.
Yeah.
Okay, so besides the drama, why was solving the cubic equation such a big deal?
At the time, it
Yeah.
was considered a major breakthrough.
Yeah.
Before that, mathematicians had only known how to solve linear and quadratic equations. Solving the cubic opened up a whole new realm of possibilities.
So it was a significant step forward.
It was.
Did they then go on to solve even higher degree equations?
Yes. In fact, Cardano's student Ferrari
Okay.
developed a method for solving quartic equations,
Yeah.
those with a degree of 4.
Okay.
But what's really interesting is that mathematicians eventually discovered that there is no general formula for solving quintic equations, or those with a degree of 5 or higher.
So there's a limit to what we can solve.
Yeah,
That's kind of disappointing.
it might seem that way.
Yeah.
But this discovery actually led to an even deeper understanding of equations.
Okay.
Galois, the mathematician we talked about earlier, who died in a duel,
Right.
developed a theory that explains why some equations are solvable by radicals,
Okay.
like square roots and cube roots, and why others aren't.
So even though we can't always find a neat formula,
Right.
we can still understand the underlying structure of these equations through Galois theory.
Exactly. Galois' work laid the foundation for modern algebra and the concept of a Galois group, which, as we've discussed, is central to the Langlands program.
Okay, so we've gone from Cardano's cubic equation
Yes.
to Galois' revolutionary theory, which connects back to the Langlands program.
Yes.
It's like we're starting to piece together a historical puzzle.
Right.
Are there any other concrete examples that might shed light on the program itself?
One of the most compelling examples is the connection between modular forms and elliptic curves.
Okay.
It beautifully illustrates the power and depth of the Langlands program.
Okay, I'm ready for another mind-bending concept.
Right.
Tell me about modular forms and elliptic curves.
Modular forms are these fascinating mathematical functions that exhibit remarkable symmetry properties.
Okay.
They're defined on the upper half plane of complex numbers, and they transform in a very specific way under certain transformations.
Okay.
They're like mathematical kaleidoscopes, exhibiting intricate patterns that repeat themselves in fascinating ways.
Intriguing.
Yeah.
But what about elliptic curves? What are those?
Elliptic curves are geometric objects defined by cubic equations.
Okay.
They pop up in various areas of mathematics, including number theory and cryptography, and have a surprisingly rich and complex structure.
So how do these seemingly different things, modular forms and elliptic curves, relate to each other? I'm guessing this is where the Langlands program enters the picture.
You got it.
Okay.
A famous conjecture called the Taniyama-Shimura conjecture, which was later proven as part of the proof of Fermat's last theorem.
Wait, are we talking about Fermat's last theorem? Yeah. The one that took centuries to solve?
The very same.
Wow.
The proof of Fermat's last theorem relied heavily on the Taniyama-Shimura conjecture, which is a specific instance of the Langlands program at work.
So the Langlands program isn't just some abstract theory.
No.
It has actual implications for solving some of the most challenging problems in mathematics.
Absolutely. The connection between modular forms and elliptic curves has profound consequences in number theory, cryptography, and potentially many other fields.
Wow. This is really making me see the broader impact of the Langlands program.
Good.
But the outline for our dive also mentions some new research directions. Like the non-abelian Fourier-Mukai transform. Honestly, I have no idea what that even means.
Of course.
Can you shed some light on that?
Remember how earlier we talked about the idea of the Fourier transform, which essentially decomposes complex functions into simpler building blocks?
Vaguely.
Like breaking down a musical chord into its individual notes?
Yeah, I vaguely remember that.
Well, the non-abelian Fourier-Mukai transform aims to generalize this concept to non-abelian groups.
Okay.
If mathematicians can successfully develop this transform, it would be a major breakthrough in the Langlands program and allow us to study even more complex mathematical structures.
Okay, so it's like taking the concept of breaking things down into simpler parts. And applying it to a whole new level of complexity.
Exactly.
Yeah.
And speaking of complexity, there's another fascinating area of research related to the Langlands program, something called W-algebras.
W-algebras?
Yeah.
Those sound pretty intimidating.
They might sound a bit daunting.
Okay.
But essentially, W-algebras are algebraic structures that play a crucial role in conformal field theory. That area of physics we touched on earlier. They're related to the symmetries of these theories and turn out to have deep connections to the Langlands program as well.
So it's like W-algebras are another thread connecting the abstract world of mathematics to the physical reality of conformal field theory.
Precisely. They offer a window into how the Langlands program might manifest itself in the physical world.
This is amazing.
Yeah.
It's like every time we peel back a layer of the Langlands program, we find even more connections and complexities. The outline also mentions something called categorification. Can you explain what that is and how it fits into all of this?
Categorification is a really interesting concept in modern mathematics, where you replace individual mathematical objects with entire categories. It's like shifting your focus from a specific species of bird to the entire ecosystem it lives in.
I can kind of picture that. But how does categorification relate to the Langlands program?
Mathematicians are using categorification as a tool to gain new insights into the Langlands program and its connections to other areas of mathematics. It's like putting on a new set of glasses that allow us to see the program in a whole new light, revealing previously hidden connections and patterns.
So categorification is essentially providing a broader, more holistic perspective on the Langlands program and its place within the larger world of mathematics.
Exactly. It's allowing us to see connections that were previously hidden and to develop a deeper understanding of the intricate tapestry of mathematical relationships.
This is all incredible.
I know it is.
It feels like every step we take in the Langlands program leads to even more fascinating discoveries. But I have to admit, my brain is starting to feel a bit overloaded with all of this complexity.
I understand.
Perhaps we can pause here for a moment and pick up the rest of our exploration in part 3.
That sounds like an excellent plan.
All All right, we're back for the final leg of our journey into the Langlands program.
Okay.
We've explored its historical roots,
Right.
seen how it connects seemingly disparate areas like number theory and geometry, and even glimpsed its potential impact on physics.
Yes.
What's next on this mathematical expedition?
We've talked a lot about the overarching concepts.
Okay.
But to truly appreciate the depth and elegance of the Langlands program, it helps to look at some of the specific mathematical objects that play key roles.
Okay. I'm all for getting a bit more concrete.
All right.
What kind of objects are we talking about? Can you give me something I can try to visualize?
Imagine a space, a kind of mathematical landscape, where each point represents a different mathematical object.
Okay.
Think back to our museum analogy, where each exhibit showcased a different equation or function.
Right.
This time, instead of a museum picture, a vast, infinite grassland.
Okay.
That's the affine grassmannian.
Okay. I can picture that.
Good.
But why a grassland? And what makes this affine grassmannian so special in the context of the Langlands program?
Like a real grassland, the affine grassmannian has a rich and complex structure.
Okay.
It turns out to be intimately connected to the representation theory of groups, which is another key aspect of the Langlands program.
Okay.
Remember how we talked about galois groups capturing the symmetries of equations?
Right. It was like a code that revealed how you could rearrange the solutions to an equation without changing its fundamental structure.
Exactly.
Okay.
Well, the affine grassmannian helps us understand representations of groups, which are ways that groups can act on vector spaces. It's like having a set of tools that allow us to dissect and analyze the inner workings of groups.
Okay, and why are these representations so important? What do they actually tell us about the groups themselves?
Representations are crucial because they reveal the hidden structure and properties of groups. It's like shining a light on a diamond to see its facets and how it reflects light.
Okay.
Through representations, we can understand how groups behave and interact, which is fundamental to many areas of mathematics.
I see. So the affine grassmannian is like a key that unlocks the secrets of groups and their representations.
It is.
And where does the Langlands program fit into all of this?
This is where it gets really fascinating.
Okay.
The affine grassmannian, with its connection to representations, leads us to another crucial concept.
Okay.
The Langlands dual group.
Okay.
It's a kind of mirror image of the original group.
Mirror image.
Yes.
So it's like looking into a reflecting pool and seeing a reversed version of yourself.
That's a good analogy. The Langlands dual group is like a reflection revealing hidden symmetries and connections that might not be apparent in the original group.
Okay, so we've got this affine grassmannian helping us understand representations.
Right.
And then we have this dual group, which is like a mirror image of the original.
Yes.
I'm sensing a connection to the Langlands program here.
Good.
But I'm not quite seeing it yet.
The Langlands program predicts a deep and profound connection between the representations of the original group and the representations of its dual group.
Okay.
It's like saying that by studying the reflection, we can learn something fundamental about the original object.
Wow, that's pretty mind-blowing.
I know.
So the Langlands program is suggesting that these seemingly separate worlds of representations are actually intimately connected.
Exactly.
Wow.
The Langlands program postulates that understanding the interplay between a group and its dual through their representations can unlock deep mathematical truths.
This is incredible.
It is.
It's like the Langlands program is revealing hidden connections and symmetries everywhere we look. But I have to admit, it's all still a bit abstract for me.
Sure.
Can you connect this back to the real world somehow? What's the point of all of this?
That's a great question. It's easy to get lost in the technical details.
Right.
But ultimately, the Langlands program is about uncovering profound connections between seemingly disparate areas of mathematics, potentially physics.
Okay.
It's a framework that's helping us see hidden patterns in relationships, leading to new insights and discoveries that have far-reaching implications.
So it's not just some intellectual exercise.
No, it's not.
It has the potential to reshape our understanding of the universe.
Absolutely.
Okay.
While some applications are still theoretical, the Langlands program is already impacting fields like number theory, geometry representation theory, and even physics.
Right.
And we're only just beginning to explore its full potential.
That's pretty exciting.
It is.
It sounds like we've only just scratched the surface of this vast mathematical landscape.
We have.
Yeah.
The Langlands program is a vibrant and evolving area of research, and there's still so much more to discover.
Wow.
What we've explored today is just a glimpse into the beauty, mystery, and far-reaching implications of this profound idea.
Well, this has been an incredible journey.
It has been.
We've gone from solving basic equations to exploring the frontiers of mathematics, all thanks to this profound idea of unexpected connections.
I agree.
Who would have thought that groups, symmetries, and even reflections could hold the keys to unlocking such deep mathematical truths?
It's truly remarkable how the Langlands program illuminates the hidden tapestry of the mathematical universe.
Right.
And the most exciting part is that the journey of discovery is far from over.
That's a great point. It's like we've been given a map to a vast and uncharted territory, and it's up to us to explore its hidden wonders. So to everyone listening, if this deep dive has sparked your curiosity, keep exploring, keep asking questions, and who knows what incredible connections you'll find.